Good morning, everyone. Hope all is well. Hope everybody's doing all right. Yeah, hope everybody had a great weekend and ready to get this one started. All right, let's see. So last class we closed out 2-4. Oh, somebody else coming in. Let me get that. So let's go to 2-5.
This is where we're.
Yeah, this is where we're going to start.
All right.
Yep. All right, so 2.5 is graphing, or basically dealing with the transformations of our graphs, and we have six basic or six parent functions. And this section explores the transformations of them, shifting to the left or right, up or down. And so I'll scroll up in a second. We see how we have the first one is our linear equation, just a straight line. Second one is our parabola. And notice how all of them going through the origin. These are, like I said, our basic and our parent functions. Then we have our cubic equation. Then square root, cube root, and then the absolute value, which gives us a v. All right, so the summary is supposed to be on page 291. At least that's last time I checked. If by some chance it changed, it still should be in that section. And it just gives you details on what it means for, if you were to add, let's say, let me scroll up. If we take this x squared, if I were to add 1 to it, what does that do to it? If I were to put 1 inside the square, add 1 inside of the square, what does that do to it? If I were to subtract 1, and so on, so each one of those would do something different, either move up, down, right, or left. And so we're using graphing tools. If we were doing it by hand, then I would spend more time on it. But we're using graphing tools. Whether it be your TI, I think Casio has one. They have plenty of graphing calculators out there. But if you don't have one, you don't have to purchase one. All you have to do is Google graphing calculator or graphing tool, and then use those, type in the function, and you'll get the graph. Desmos is one of them that's online, a website that you can use. And you can plug these in, see how they see how the transformations affect the basic function, and so on. So, like I said, if you were if the requirement was for you to do it by hand, then we would spend time on it. But you guys are pros at graphing at this time, at this moment. So they really don't focus on you graphing by hand, but make sure you do have something reliable that you can use, so that you can be able to compare these graphs and see how they shift up, down, left, and right. And like I said, the summary is on page 291. That lets you know the difference between the 4 scenarios that I just gave. And you have any questions on it, feel free to ask. It's not a big deal, but don't spend too much lecture time on it. Like I said, just throwing it in the calculator and looking at the graphs. All right, anybody still holding on to this before I scroll up? All right. Am I good with the red? All right. So 2.6.
Hang on, can you go back down just a little bit for the red?
See, I say, are you good with the red? And nobody said nothing, but did not just
I was shaking my head. No, man. I was trying to get to the mute button.
You know what?
You're
It's
good right
funny.
there. Thank you.
It's weird because I had, for some reason, and I guess it just depends on how Zoom feels. Sometimes I can have my class up, but then when I touch my screen, the class disappears and I can't see anybody while I'm writing. But other times the class just stays up there and I don't know how to fix it. I tried pinning it up there and everything. I guess it's just how Zoom feels at that point in time. So I couldn't see you. So my apologies on that. So yeah, but you're
All right,
good.
I'm good. Thank you, sir.
Okay, cool, man. You know, probably, you know, I just mess with you because I can.
Oh, absolutely. Absolutely. It's welcome.
So 2.6, combinations of functions and composite functions. All right, so is everybody done with the red? Make sure we're good, good. All right, so when we look at the first thing that they want us to do in this section is finding the domain. And I believe we talked about the domain before already in this class, not mistaken. Yeah, this class. So we're talking about all the values that can be used for X. That's what the domain represents for us. All of the values that we can use for X. Or in other words, all the values that can be plugged into the equation for X. So we're talking about what can be used for X, talking about values we can plug into the equation for X. All right. So key for us to being able to find the domain, we will look for the values that cannot be used. It'll be easier for us to figure out what values that we can use by looking for the values that we cannot use. So first exercise, find the domain of each. They give us first f of x is equal to x squared minus 7x. So you ask yourself the question, is there a value that can be plugged in for x that will make the equation undefined? So you want to know, is there anything I can plug in for x that will put me in a bad situation as far as the equations are concerned? In other words, it will make the equation undefined. Now for this scenario, we have this parabola for x squared minus 7x. The answer is no. There's nothing I can plug in for x that will make it undefined. Of course, I'm going to show you some examples of what that is, what that will look like, what type of equations will set that up for us. But in this scenario, there's nothing I can plug into it to make it undefined. If I plug in 0, 0 squared is 0, 7 minus 0, 0, 0 minus 0, it's still 0. 0 is a valid number, so there's nothing wrong with that. Plugging in 1, 2, anything you plug into this equation will work out fine. It will give you a legit number. So there's nothing you can plug into this equation or into this function to make it undefined. So your domain is just negative infinity to infinity. So that means you can use all real numbers and not have an issue. All right. Scrolling up.
And what exactly do you mean by make the equation undefined?
That's what we're about to get into next.
Okay.
Yep. So I'm gonna show you some examples of where that will be the case, and you'll see the difference. All right. So going into the next one, g of x is equal to 2 over x minus 5. Here we have a rational expression, right? A rational expression is the same thing as a function. I mean, as a fraction. Fraction, rational expressions, same thing. So can I make this fraction undefined? The answer is yes. Fractions are undefined when the denominator is 0. So see the difference between this situation and the last one. The last one didn't have a type of scenario that would make that function undefined. I could plug in anything. Now, for here, because I have a fraction now, I cannot have 0 in my denominator. That's the situation that comes with all fractions. So if I have 0 in my denominator, then my answer is undefined. So what you can and cannot do always be determined by what you're given as a function. All right. I think we're done with that first one. So whenever you have a fraction, this means you're going to set the denominator equal to 0 and solve it if you want to find the domain, that is. Set your denominator equal to 0 because you want to know when is your denominator equal to 0. That'll let you know where the problem is when your denominator is equal to 0. So x minus 5 equals 0, add 5 to both sides gives us x equal to 5. So this is the value that we cannot use. Remember, x minus 5 equals 0 is when our denominator is equal to 0. So this is the value that cannot be used. Once you find a value you cannot use, then you know all the values that you can use. And that's what happened right here in a dark purple. And I went ahead and wrote the domain. So I can use everything except for 5. So I'll write my interval as negative infinity up to 5, then 5 to infinity. Don't forget that the parentheses on the 5 means I can get as close to 5 as I want, but I cannot use 5. So that's why we use parentheses on that 5. Just letting you know you can get as close to 5 as possible on the left side, and then close to 5 as possible on the right side. You just cannot use 5. Make sure we're okay.
Can you explain that the up to 5 again? Is it because you're counting from negative infinity 5 spots? Is that why it would go to 5 and not actually equate to 5?
Well, let me make sure we on the same page though before we go there. So are you okay with the fact that we got the 5 from here?
Yep.
Okay. So now remember, if we got 5 from there, that's the number that we cannot use. Because if I use 5, I get 0 on my denominator because 5 minus 5 is 0. So you okay with that part?
Yep.
Okay. So now I need a representation as far as interval notation is concerned, a representation of all the numbers that I can use except for 5. And so that means I can go from negative infinity up to 5. That means I can use 4.9, 4.99, 4.999999. I just cannot use 5 because if I use 5, that'll give me 0 in my denominator. Now on the right side of 5, I can use 5.1, 5.000001. I can use as close as I want to use to 5. I just cannot use 5, but I can use everything else. So that's what
So,
this,
so if you find that number, it's just known that you can use any value from the left side, like you said, 4.9999, and then the other side of it, 5.1, but you can't physically use 5 because that is the number that it came out to be that you can't use.
exactly.
Okay, I got it now.
Yep. All right. And once again, just harken back to when we talked about interval notation before, that's the difference between use parentheses versus using brackets. Remember, brackets means that I can use that number. Parentheses means that I cannot use. So just throwing that back out there, throwing it back into the atmosphere, making sure we own that. All right, so let's do it one more time as far as fractions are concerned, rational expressions. We have 3x plus 2 over x squared minus 2x minus 3. Once again, it's a fraction, it's a rational expression. So I want to know, when is my denominator equal to 0? Because that's where I will have problems. Excuse me. So I want to set my denominator equal to 0 and solve it. Those are the values that will give me problems as far as this function is concerned. So this time we have a quadratic function, quadratic equation that is set up because of our denominator. So you can factor it, or once again, don't forget, you can plug it into your quadratic formula to get your two values. I went ahead and factored. Ended up getting x equal to 3 and x equal to -3. Once again, these are the values that we cannot use. Remember, these are values that will produce 0 in our denominator. So this time we have 2 of them instead of just one like we did last problem. All right. So you have to make sure we cover all intervals. So if you look at a generic number line, -1 is furthest to the left, 3 is to the right. We have to give an account for all intervals. So we were talking about infinity, negative infinity to -1, -1 to 3, and then 3 to positive infinity. And that's what I have right here. So you give an account for all 3 of those intervals. Once again, parentheses on the -1 and the 3, just signifying we can get as close to those two values as possible, just cannot use them. All right, ready for the next example? All right, so here we have the square root of 3x plus 12. So what's under the radical? This is a radical equation, radical function. And let me see if I can write that up here. We talked about this already, but just want to notate it. So that's the radical. And then what's under your radical is called the radicand. So once again, we're asking ourselves, can we make this expression or function undefined, or when is the radical undefined, the application of the radical undefined? And that goes back to our imaginary numbers. Remember, we cannot take the square root, of negative numbers. That'll give us imaginaries. Mhm. So what you need to do now is set your not your denominator, your radicand greater than or equal to 0 and solve that. Because if it's greater than 0, then we know it's positive. So we need the positive values. We just said we cannot take the square root of negatives. So we want the positive values. And it's okay to take the square root of 0. That's why we're doing greater than or equal to 0. Square root of 0 is just 0, so that's fine. We just cannot go less than 0. Less than 0 would be the negative values, which we cannot take the square root of. So whenever we're doing this, we're always taking what's under the radical, the radicand, and doing greater than or equal to 0. Solve that. We'll subtract 12 and then divide by 3. Can I scroll up some? So that ends up giving us x is greater than or equal to -4. And so we'll use a bracket on that -4 because of the or equal to symbol. Don't forget that line tells us to use bracket. And like I mentioned earlier, bracket means that I can use the value. All right, we're good. Can we scroll up? All right, next thing, the algebra of functions. Just a shorthand way. Once again, mathematics is always about giving you symbols to give you instructions to, the least amount of symbols possible, to write the least amount of words possible to get you to do something. So f plus g of x is just telling you to add both of your functions together. F minus g of x, subtract both of your functions. F times g of x, you multiply them, and then f divided by g of x is f of x over g of x. So you divide them out your functions. So. All right, scrolling up some. Oh, I didn't mention this. Of course, they're going to give you f of x and g of x, so they'll never say find f of x, find g of x. They have to establish those first. So like we see in this example, they say let f of x be equal to 2x minus 1, g of x is equal to x squared plus x minus 2. And then we're going to find each one of the 4 that I just introduced. I just want to give people a chance to copy this stuff down. But notice they do establish what f of x and g of x are. All right, and scroll up. So the first one, f plus g of x, all they gave you was this. And so from there, then you would know to do this, So you just adding your functions together, combining your like terms basically. So 2x minus 1, x squared plus x minus 2, x and 2x gave you 3x, negative 1 and negative 2 gave you negative 3 to give you the expression x squared plus 3x minus 3. And then if we were subtracting them, just don't forget to distribute that negative into that g function, turn each one of your signs opposite, and then from there combine your like terms. And that'll give us x squared, negative x squared plus x plus 1. Everybody done with A? All right, so C is multiplying your functions. So don't forget, how you distribute. Here we have f of x times g of x means 2x minus 1 times x squared plus x minus 2. So you distribute each individual term into the next parentheses accordingly. So 2x times x squared times x and then times negative 2 would be 2x cubed plus 2x squared minus 4x. Then distribute the negative 1, that'll give you negative x squared, negative x plus 2. Combine your like terms, and that'll ultimately give you 2x cubed plus x squared minus 5x plus 2. All right, so everybody good? All right, so D. So D is f over g of x, f of x over g of x. So just place f of x over g of x. Now if you could factor and things could cancel out, you would be expected to do so. In this case, there is no cancellation that will benefit you, and there is no cancellation that could occur. So you would just leave it the way you see it, 2x minus 1 over x squared plus x minus 2. Any problems, any questions? All right, one more. Now this one actually gives us a number 4x. Notice how it says find f of g of 2. And normally it says f of g of x, just generally. So what that means is that you just take 2 and plug it in where you see x in your f of g of x function. Matter of fact, let me do this. And so that's what I did right here. I just took 2 and plugged it into each one of the spaces that I have over here. So that's 2 times 2 minus 1, 2 squared plus 2 minus 2 on bottom. That'd be 4 minus 1, 4 plus 2 minus 2, ultimately giving us 3 over 4. All right. I scroll up. Everybody good? All right. The composition of functions. We used to call this fog of x and golf of x. That O is a circle. It doesn't look like the letter O, when you actually see it, when in actual text. It's just a circle. But what it means is for the function that you see second to be plugged into the first function. So this means G is going to be plugged into F. And then golf of X means that F is going to be plugged into G. So as always, the second function goes into the first function. You actually substitute in the whole function into another function. And that's what these represent over here. Substituting that second function into the first function.
What's that little circle between the F and the G?
It represents the composition. Yeah. And so that just means that's just telling us to take this G function and plug it into F. So whenever you see that circle in between your functions, that means you're going to take that second function and plug it into the first one you saw. All right, everybody done with the red, so we can try this out. All right. All right, so let's find the composition of, those relationships. Once again, you see how it's given what f of x and g of x are. F of x for us this time is 3x minus 4. G of x is x squared minus 2x plus 6. And they tell us to find fog of x. So once again, the relationship that we're emphasizing is that G is going to be plugged into F. So we're going to take this whole function of G and plug it into F where we see X. And that's what we did right here. So it was 3x minus 4. So where I saw X, I put the function of G. So that's why it's 3 times x squared minus 2x plus 6 minus 4. Make sure we're okay with the substitution. We took the whole function of G of X and plugged it into F where we saw the X. Once you do that, then you can go to simplify accordingly. You can distribute your 3x squared minus 6x minus, plus 18, then combine your like terms in the back. 18 minus 4 is 14, so that would be your expression. All right, questions before we look at the next one? Just reversing the relationship. So golf of x means we're going to take f and plug it into g. So we're going to take 3x minus 4, plug it in where we see x in the g function. And that's what happened right here. So it was x squared minus 2x plus 6. So that was 3. Now it's 3x minus 4 squared minus 2 times 3x minus 4 plus 6. All right. So now when we go to simplify this expression, don't forget, and I got it over there in the purple, you cannot just square 3x and square 4 and move on to the next thing. That's an expansion. That's 3x minus 4 times 3x minus 4. So then you have to fold that out. And that'll give you 9x squared minus 12x plus 12. Add your 12x's in the middle. That's 9x squared. Let me get this out of the way. 9x squared minus 24 plus 16. Then you're going to distribute the negative 2 right here. So negative 2 times 3x is negative 6x. Negative 2 times negative 4 is positive 8. And then you still have that plus 6 in the back. All right. After you have your expansion completed, then you can go ahead and combine your like terms accordingly. 9x squared minus 30x, that comes from 24x, and the negative 24x and the negative 6x. Then the plus 16, plus 8, and plus 6 gives you a plus 30 in the back. Any questions? All right, so see, once again, they give us a number to plug in, just like they did in the last example, previous us, doing this composition stuff, if I can say it right. Anyway, so we have one that we're going to plug in for x. So there's two ways that we can handle this calculation. The first way, remember, that's f of x that you're plugging into g. So if I have 1 for x, that means f of 1 I'll be plugging into g. So I can find f of 1 first, which is what I did right here. Remember, f of x is 3x minus 4. So f of 1 would be 3 times 1 minus 4. 3 times 1 is 3. Minus 4 is going to be negative 1. And then from there, plug in negative 1 into g. And so you see that we have this right here. That'll be negative 1 squared minus 2 times negative 1 plus 6. And that reduces down to 9. All right, so that's the first way of doing it. Now the other way, excuse me, because I have already found this, I could just plug in that 1 into there. So that's what I did here. Plug 1 into this, because remember that represents generically golf of x. So I'll plug 1 into that. So here, 9 times 1 squared minus 30 times 1 plus 30. And we see that it reduces down to 9. So either way is fine. Doesn't matter which one. You do not have to do both of them, because either way you'll get the same answer. Just showing you your options. Just showing you your options. right, are we good? Any questions? All right, are we good? So we're going to start 2.7 and stop. Just want to introduce inverse functions, but I didn't want to get too heavily into it and then have to stop in the middle of a part. So I'm gonna get to a good place to stop, but at least want to introduce inverse functions. So then we won't have to worry about introducing the next class, and we'll go from there. So inverse functions, if we let f and g be two functions such that when I plug g into f, going back to what we just finished doing, plug g into f, it reduces down to x. Then if I were to plug f into g, it would also reduce down to x. Now, keep in mind, both of these have to happen in order for us to have inverse functions. It's not just one or the other. So you will have problems wherein when you plug g into f, it'll reduce down to x, but then when you plug f into g, it would not. So you do have to check both. So you cannot take it for granted that one worked, that means the other one was going to work. So they both have to happen. And you do have to check both. So if this do occur, g is the inverse function of f. And then our notation is right here. Notice we have f, and then we have the -1 like an exponent f. That's called f inverse of x. So that would be the notation of your inverse functions. All right. Scroll up. Oh, also that statement, another general statement. The domain of f is the range of f inverse and vice versa. So when you talk about the inverse function and the function itself, the domain and range will switch. All right. Tell me where I can stop if I go up too far. So in the green, we have our first exercise or something they may ask you to do. Show that the functions are inverses of each other. So remember what I mentioned, the only way you know if functions are inverses of each other is if when you have to plug one into the other, it reduces down to x, and then plug the other one into it as well in reverse order, I guess you would say, and that reduces down to x as well. So both transactions have to reduce down to x in order for them to be inverses of each other. So here we have 3x plus 2, and then x minus 2 over 3. So the first one I did, doesn't matter which one you do first. First one I did was I took G and plugged it into F. So I realized right here. All right. So that's 3 times x minus 2 over 3. 3's cancel. Leaves me with x minus 2 plus 2 That allows my 2's to cancel, leave me with just x. All right. Everybody okay with that first one? Now you have to take F and plug it into G. Okay, I heard somebody unmute. Are we good? Okay. So now we're going to take F and plug it into G. So that's what I did down here. Now I just use the parentheses right there for 3x plus 2 just to signify that that was the function, but there's nothing holding those parentheses there. So 2 minus 2 can cancel, and that leaves you with 3x over 3. 3's can cancel and leaves you with x. So once again, plugging G into F, reduce down to x, plugging F into G, reduce down to x as well. That proves that both of these functions are inverses of each other. All right. Problems with that? Make sure we're okay. All right, so last thing for today. I think Miss Dawn will appreciate this one right here. Here go your horizontal line test in a second. So we have a one-to-one function. Each element in the domain goes to exactly one element in the range and vice versa. So remember, when we're just talking about a function, just a regular function, remember we could have repeated values in the range and not the domain. It was just the domain that went to exactly one value in the range. Well, if you're talking about a one-to-one function, only one can go to one. So there are no repeated values anywhere. So being one-to-one or not being one-to-one doesn't stop it from being a function. It's just saying it's not a one-to-one function. And so the reason why this is important, you see that in red, if the function is not one-to-one, then it does not have an inverse. It does not have an inverse. If it's not one-to-one, it does not have an inverse. All right, so the way we will be able to test that one-to-one relationship is by the horizontal line test. Remember before we had the vertical line test? And if you remember the vertical line test, then the horizontal line test is the exact same way, it's just that it's horizontal. So it says if a horizontal line crosses or touches the graph more than once, then it is not one-to-one. All right. Yeah, I'll go back up in a second. Back up in a second. This is the last thing. Yep. So once again, if your graph crosses a horizontal line crosses the graph more than once, then it is not one-to-one. So if we look at our generic straight line linear equation, notice how horizontal line only touches it once, no matter where it goes. So that is one-to-one. Parabola is not one-to-one. Draw a horizontal line through it. Notice it touches it twice. And so notice I wrote the two statements there. It is not one-to-one, but it is still a function. Remember, we found out but from the vertical line test that a horizontal, that a parabola is a function, but we just found out that it's not a one-to-one function. So once again, that is important because that means it does not have an inverse. And then your cubic equation is one-to-one. No matter where you draw the horizontal line, it only touches it once. Questions or anything?
I have a question.
Mm-hmm.
Oh, why is there like no 2.5 and no 2.6?
You said no 2.5?
Yeah, and 2.6.
Well, we did 2.6. That was what we just came out of with composition of functions, algebra functions. So that was all 2.6. 2.5, I talked about it, but I didn't do a lecture on it because it's all graphing, and I said use a graphing tool or a graphing calculator.
Yeah.
And so I said that if you can't figure out, what to use or how to use it, or if you have any questions about 2.5, then feel free to ask. But since we're not making you graph it by hand, there really wasn't much for me to discuss. I just, laid the foundation, and then we went into 2.6. And so this is 2.7. Say again now.
It just doesn't show like where, like, you know how like it shows like all the different ones on the side thing, like which one you're in.
Oh, you talking
Like,
about you talking about my stuff on the left?
Yeah.
Oh,
Yeah,
that's for me. I didn't even know y'all were even looking at that. And so in there, so like I started that set of notes, like this set of notes right here, it started with 2.4 and I kept going. And then this one starts with 2.7. You see what I mean? Like, so yeah, I had never even thought about you guys looking at that right there. That was just me and my stuff going on. So it's just like a marker for me to let me know how I started. So I know that this one right here, 2.4, that's labeled 2.4. If my next set started at 2.7, that means in that 2.4 notes, I have 2.4, 2.5, and 2.6. And then the next one starts at 2.7 and have 2.8. It's just, what I decided to write. Yeah. So I didn't, like I said, I didn't even think about referencing that to you guys because that was just me and my stuff, So
Okay. Thanks.
Yeah, not a problem.
Can you scroll so I can see the bottom, please?
Okay, maybe it's just me because I have a lot going on and I don't know. I just feel like, can we just slow it down just a little bit? Like, I don't know. I just feel like it's just a lot coming at us all at once right now.
You know what? I tried that and somebody told on me. I mean,
but yeah, I saw that video.
I mean, I tried. And so, cause like, if I did it my way, like, cause I have two 161s back to back. Now I was stopping right here because I know most definitely I wasn't gonna throw any more on you. But I have two 161s back to back. So when I did my last class, I was just like, dang, I wanted to stop. I didn't even want to go into 2.7, but that was like only a half an hour of lecture. And I didn't want to go back to the principal's office. So I was
I seriously doubt it was anybody in this class. I feel like what you were doing before was working for all of us.
Right. And so, but see, this is the funny thing about it. I even asked the dean, can you at least tell me what class it's in? Because I know telling me the student would be like a breach of confidence, blah, 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 whatever. You know what I mean? And it's not like I'm gonna attack the student anyway. So I didn't even care who the student was. Can you at least tell me the class so I know how to handle that class? You know what I mean? Because that means everybody else was good. But he never emailed me back. So I'm just like, all right, well, I don't know who it was. So I got to try to at least, you know what I mean? I just don't know how. it puts me in a funny space because I don't know how to handle, you know what I mean? Because what I don't want, because the person never
Right.
talked to me. So
Mhm.
I don't know how to address that person's issue. So I don't, I mentioned that in the video. So it's like I'm in this weird space where I'm trying to consider everybody, but I do know if that person go back to the dean again, then it's gonna be trouble for me. And I'm just like, but I'm just looking out for y'all, like, so it's just a weird space. But if you guys but I'm gonna try to do my best. And there will be moments where we won't even do anything. Like we coming out, closing out chapter 2. There's gonna be a
Right.
day when I'm not gonna do anything new, period, anyway. So I understand, trust me, I understand. I'm just trying to stay out of the principal's office because I just went in there. So I'm trying not to go right back. You know what I mean?
No,
So,
I understand.
try to give me a little bit of break. I'm just trying to figure
Let's
this
take
thing
a
out.
class vote. Is he going too fast, too slow? Where we at, y'all?
Right. So, but look,
I
with
think
that
you
being
should do like a
said,
30-minute tutorial on how to use the graphing calculator so everybody's up to speed on that. I think that
everybody
would
up
be
to
a
speed.
good, I
Yes,
mean,
please.
something we could all handle right now.
Right.
Because you just threw out a bunch of Mandarin Chinese all of a sudden. Like, bro.
So
I seriously spent 13 hours yesterday trying to go over and complete all the homework and watch the lectures from last week. It was 13 hours.
wow.
Like I'm mentally, I wanted to quit. I hate math.
Oh yeah, when I look at how long I've spent on all the homework collectively, it's depressing. It really is.
See,
Agreed.
everybody agrees, man, but I just don't know who it was. I just don't know. And you know what? I was joking with my sister. It's funny that somebody that could be the most vocal about it could be the one who actually did it, but they're trying to make sure that they just fall with the crowd. You know what I mean? I don't know, man. So, but we were gonna stop right here. We were gonna stop right here for today. And we're gonna try to pace it back out. Like I said, I just at least want at this point, it just happened last week. So I was trying not to give give that person some more ammunition. You know what I mean? So because remember I'm recording the videos and it don't go all the way to the
Just
end.
give
So
us the dean's email. We'll take care of the rest. All of us are willing to send an email right now. I promise you, it's going to be a much more positive experience for you. I promise.
right.
Got you.
All right, I appreciate it. Well, let's try. Let's see if we can just pace it, and then if it comes to that, we know what we need to do. So yeah. With that being said, anybody have anything before we go and close out today?
Hey, I will tell y'all, if y'all can make the time to go into his office hours, it is very beneficial because it's a smaller group of people and you can get a bunch of questions in and out and it's easier to explain. So if you can make the time for that, I highly recommend it because it is very helpful.
All right. Somebody asked me, can I go back here? Copying the stuff. All right.
If-
Anything else?
If not, may I go?
Huh?
If I don't have anything else, may I dip?
Oh yeah. That's what I was about to say. So if you guys are good, I'm good. Have a good one. Be safe, and we'll come back next class. What we'll probably do is close out 2.7, the rest of 2.7 and 2.8, just to get them out the way, and then we'll look and see how we're going to handle the rest of, whether we're going to have a review day where we won't be doing anything at all, and then if we need 2 review days, that would be, we'll see how we work that thing out and go from there. All right. So you guys have a good one. Be safe, and I will see you next class.
Thank you.
You have a nice day.
Today, I'll be there.
Take care. All right. Sounds good. See you in a few.
Thank you.
All right. Take care.
Yeah, I'll see you this afternoon, man.
All right, man. Sounds good.
Well, we got a little bit more work to do now. You just fried my brain all of a sudden.
No problem. You got those jackhammers out of the way?
Bro, my head was rattling for like 2 days. It was nonsense. My poor neighbor, I feel so bad for you, man. He was like, I forgot you were doing school. He was like, he was real cool about it because you went out there and yelled at him after they started back up. He was like, nah, man, if he's doing his schoolwork, y'all ain't getting jackhammer or nothing.
Wow.
But
that's cool to have somebody.
he was
to
cool,
look
so I
out
had
for
to
you.
let him do it.
Yeah.
And they were out there for like 10 hours,
Woo.
just going to town, dude. And then after the jackhammering, because he's hardscape in the backyard, so they had to run the tamper like multiple times so they could tamp the ground to get everything compact. So like it's just shaking all the glass in the house and everything. Like my computer was rattling on the table.
Wow.
And I
That's
had
crazy.
I had 3 quizzes and 3 papers of 500 plus words to get in for stupid SDB class this weekend,
Wow.
which smoked me on time. So yeah, a 1 credit class taking that amount of time is nonsense.
Yeah, that's crazy. That's crazy.
Yeah.
Well, I'm
All
glad
right,
it's
man.
over,
I'll see you
man.
this afternoon, man.
Yep. Take care.
Appreciate it, bud.
Yep. All right, Mr. Best. Are we good? Let me know when you finish. Okay, yeah, not a problem. Not a problem. You have a good one. Take care.